Okay, so the next property of Fourier transform that I want to go through is something called as convolution. So let me write it down. So number 3 is convolution, is an operation. Okay, so we define the convolution as the Fourier convolution as, so the convolution of two function is defined as f star g, so two functions like f and g. So the convolution of them is defined as this integral of minus infinity to infinity of f(x) minus Kessi times g Kessi and d Kessi. Okay, so this is just a definition, how we define Fourier convolution, and this also equals to g star f, right? So you can just change the order of these two. And this is the definition of convolution. And there is a reason we define this, because the multiplication in the regular space is gonna be a convolution in the Fourier space. So let's see this fact by defining, starting these Fourier transforms. So let f hat be the Fourier transform of f, and g hat be the Fourier transform of function g. Okay, so these are just the definitions we had before. Here, for example, is the Fourier transform, and by Fourier transform we mean this integral transform that you see here. Okay, so let's have these Fourier transform, and now I want to calculate the Fourier, the inverse formula, the inverse Fourier of f hat times g hat. Okay, so this is gonna be based on the definition 1/2 pi of integral of minus infinity to infinity of any function that you put inside, right? So this is the inversion formula for f(x), right? And then you are gonna get f hat beta, right? So we have to have that function in the Fourier in the omega space. So we have f hat beta now, g hat beta, e to the power minus i.beta.x d beta, right? Let's check it here. So this is the inversion formula. Yeah, we have e to the minus i.beta.x and f hat of beta. Okay, so this equals to the integral of minus infinity to infinity. I just rearrange the terms. I'm gonna get f hat beta of e to the minus I beta x, and then what I'm gonna do is the rearrangement of these, I'm just gonna write the formula for this. So I'm gonna write 1 over 2 pi integral. Instead of g hat beta, I'm just gonna write the definition of the Fourier transform, which is gonna be gy e to the power I beta y dy, and then I have d beta here. Just rearrange the terms and wrote the definition of g hat beta. And then I'm gonna again rearrange these, so I'm gonna write 1 over 2 pi. I'm gonna do the integrals together, integral of minus infinity to infinity of gy e to the power I beta y f hat. The second integral, I'm just gonna combine these two, f hat beta, and I can do this because I can bring this inside because this is not a function of y, right? So f beta, and then I can write e to the minus I beta, combine the exponentials. I'm gonna get x minus y, right? And then I'm gonna get d beta for the first integral and dy for the second integral. This is just a combination of the integrals, or we can say the interchange of to interchange the order of integrals. So now I want to interchange the order of these integrals, and what I'm going to get is the integral of minus infinity to infinity of gy 1 over 2 pi integral of minus infinity to infinity of f hat beta e to the power minus I beta x minus y d beta and dy. Okay, so this is just rearrangement of the terms and changing the order of the integration. So first I'm gonna integrate over here, and then the rest terms, these terms, I made a mistake here. Let me just correct it. I have a mistake. I already wrote it here, so I don't need to write the e to the I beta y again. So, and then the second term, I'm gonna put it here as the second integral. Right, so I just rearrange these two integrals, the order of these two integrals, and I'm gonna get these formula. So here is times, so they are multiplied by each other. And what I'm gonna get here, there is an interesting thing here, because when you interchange the order of the integrals, and that is this function that appears here. What it is? Can you remember that? So if you look at the formula for the inversion, if you have x here, then you're gonna get fx, right? So anything in place of x is gonna get me fx. So for example, if you have y here, if you have e to the minus I beta y, you're gonna get fy, right? And this is just an inversion formula. So we have the same thing here. This is just the inversion formula. And here, instead of x, I have x minus y. So this is just gonna be the inversion formula for f, so it is just fx minus y. Interesting. And then this reduces to integral of minus infinity to infinity of gy fx minus y dy, right? And this is based on the definition that we had for convolution, right? This is, rather than like Casey, you can just write y. This is just the convolution of f and g. So interestingly, we started from here, from this equation, inverse of f and g, and we got to here. So this means that the convolution in the regular space is nothing, just this the inverse of the inverse Fourier transform of f hat and g hat. So let me just write this down. So this means that the f minus 1, the inverse Fourier transform of f hat g hat equals to the convolution of these two functions. And I can get a Fourier transform of the both sides of these equations, and I'm gonna get the Fourier transform of minus f hat g hat, the left hand side, equals to the Fourier transform of the right hand side, f g convoluted by g. So this one is just what? You take the Fourier transform of the inverse Fourier transform, so you're just going to get the original functions. So this tells me that f hat g hat is the Fourier transform of f star g. So, or let me write it the other way. I think that is better if I write it the other way so you understand it better. So in other words, when you take the Fourier transform of the convolution in regular space, you are gonna get the multiplication in the of those two functions in the frequency space. Okay, so let me write this down. This is also gonna make our lives easier to some extent when you have integration. So this tells us that integration in X space, which can be hard, right, if you have integration, or regular space, becomes multiplication and by integration we mean this, for example, minus infinity to infinity of f mac x minus epsilon, or Casey g Casey d Casey, becomes multiplication in the beta space or frequency space, which is easy, right? And this is just f hat g hat, the multiplication. So as we saw, the differentiation becomes multiplication in the regular space, becomes multiplication in the Fourier space, right? So let me write it down in other ways. So here, if we have this, the other way of writing it is minus I beta power k of f hat, right? And we saw, and this is equals to f of f times Fourier transform of g. So the convolution, this integral in the regular space becomes a multiplication of those two functions. And there is another thing here. So this is just going to make it easier, but in some cases, if you have, for example, two functions that are multiplied by each other in the regular space, okay, those two functions become convolution. The multiplication in the regular space becomes convolution in the Fourier space. So let me show this down. And what I'm gonna trying to say is, for example, if you have two functions that are multiplied by each other, f, g, in the Fourier space, they become convolution. So let me see if I can show this here, just briefly. So if you take the Fourier transform of these two functions, you are gonna get the integral of minus infinity to infinity of, based on the definition that we have, is gonna be, yeah, e to the I beta x and f e to the I beta x and fx dx, right? So fx gx dx, and you can show that this is gonna become convolution in the Fourier space. Okay, so I'm not gonna go through that, but you can show that this relationship also holds by putting this into the definitions of this convolution that we have. Okay, so this was about convolution, and one thing I want to note is, as you see, if you have integration or differentiation in the regular space or X space, then using Fourier transform is going to be beneficial for us to solve these PDEs, because they will be reduced to just multiplications. So integrations and differentiations in the X space will be reduced to multiplication in the Fourier space, and so they will become easier to solve in the Fourier space. Okay. So another property of this Fourier transforms is X shift. So that is, if you want to shift X, I want to show what's going to happen. So the inverse Fourier of e to the I so if you shift x, let me write it this way. So if you shift x, fx minus a, in the Fourier transform, you will get just this e to the I a beta and then multiplied by the Fourier transform of that function. So this will be the effect of x shift. So you will just have 1 e to the I beta that you need to multiply by your function, by your Fourier transform. And the proof of this is very easy. So let's get started. If x minus a is 1 to 2 over 2 pi of minus infinity to infinity of e to the minus I beta x minus a f hat beta d beta, right? So this is just the inverse formula that we have here. Instead of x, I just write x minus a because we have changed the argument. So this is gonna be 1 over 2 pi, the integral of minus infinity to infinity, e to the power I a beta, right? Let me write it this way. Minus i.a.x, right, times e to the i.a beta f hat beta times d beta. Okay. So let me add one more page. So as you see, this equals to the inverse Fourier transform based on the definition of this function inside it. So it's the Fourier transform of i.a beta f hat beta based on the definitions that we had. And so this expression is proof. So this one. Okay, so an x shift and a shift in the x space in your argument is gonna cause, we need to multiply e to the i.a beta in the Fourier space, okay? And the last property that I want to note is beta shift. So let's see what is gonna happen if you have a shift in your argument in the beta space or in the Fourier space, frequency space. So if you have that, you are gonna get f minus 1 of f hat beta minus b, I would say, instead. So we have b shift, we're gonna get e to the minus i.b.x in the x space. So when you shift your frequency or beta in the Fourier space, you are gonna get, you have to multiply your function in the regular space by e to the minus i.b.x. Okay. So let's prove this too. So I'm gonna start with the left hand side, f minus 1 f hat beta minus b. The definition of this I'm gonna just write down 1 over 2 pi integral of minus infinity to infinity of f hat beta minus b e to the power minus I beta x d beta. So this is just a definition of inverse formula. I just wrote down in terms of the integral. Okay, and then I define this new variable nu as beta minus b. Okay, so beta is gonna be nu plus b, and d beta is gonna be d nu, right? So b is constant. So I'm just gonna substitute this into the integral that I have. So I'm gonna get 1 over 2 pi integral of minus infinity to infinity of f hat nu times e to the minus I nu plus b x d nu instead of d beta, right? And because b is constant, I can take this out here. It doesn't matter, right? So I can just write it down as e to the minus i.b.x. It's not a function of nu, right? So i.b.x times 1 over 2 pi integral of minus infinity to infinity of f hat nu times e to the minus I nu x d nu. And this is what? This is just the inverse formula. So I'm gonna just get back f nu here, if you look at the definitions that we had. So this is gonna lead to e to the minus i.bx times, sorry, this you are gonna get here fx in the regular space. So we are gonna get e to the minus i.bx times fx. And this is gonna prove our claim here, that the shift in the beta space or frequency space, we just need to multiply that by e to the minus i.bx in the regular space. Okay, so these were some of the properties of Fourier transforms that you need to know. So let me just give a brief overview of what we studied for this lecture and what we found. So we defined in general integral transforms, you can transform a PDE into a different space like Fourier space, or different types of integral transforms that we have, like Laplace transforms. And then we solve the transform equation in that space, because those transforms are going to simplify our equations in the transformed form. And then we transform the solution back into the regular space, so we have kind of solved our PDE. Okay, so this is the basis of and the reason why we are using these integral transforms. And so I only introduced one type of integral transform in this class, and that is complex Fourier transforms. But just know that there are other types like Laplace transforms and also even finite Fourier transforms. So, and then we showed that we can write any function with these specifications in terms of this formula. And this formula we define as a Fourier transform pair with an integral transform, forward integral transform, where we take the function into the Fourier space and an inverse of that, and the inverse of that, where we take back the function from the Fourier space into the regular space. Okay. And then we define some properties of that. So this is just a note for your reminding you, and as a reminder. And then we define some properties of Fourier transforms like linearity, right? So this you can just add two functions together, and there is a linearity relationship for that in the Fourier transform. And the other two important points were that differentiation in the Fourier space, in the regular space, is going to lead to multiplication in the Fourier space, right? So it's going to make it easier. And also we define convolution operator in Fourier convolution in the Fourier space, and then we showed that multiplication in the X space is going to lead to integration in the X space is going to lead to multiplication in the Fourier space, right? So this was another advantage of using Fourier transform. So if you have difficult high order derivatives or difficult integrations in your regular space, it's better to convert them into a Fourier space and then solve the equations in the Fourier space and then take it back to regular space. Okay, and finally, two other properties. If you have an X shift, what would be the effect of that on in the Fourier space? And if you have a beta shift, what would be the effect of that in the X space, regular space? So these were just these two expressions. And in the next lecture, what I'm gonna do is I'm gonna solve one PDE with in the next lectures. I'm gonna solve some examples of these by converting a PDE into a Fourier space and then solving the solution in the Fourier space and transforming it back into the regular space. And so this will give you an additional way of solving the equations in the Fourier space. And other than that, even in some of the numerical codes, we convert these differentiations and our equations into a Fourier space. We take them to a Fourier space and solve these numerically in the Fourier space. And the reason for that is we are gonna get very, very accurate results if we do that, because our differentiations are gonna be almost exact, almost accurate. So for example, and we are going to talk about this later on, if you have like du over dx, if you want to solve this numerically, and again I'm gonna go through this very thoroughly later, just I want to give you the idea why these are very useful. So you can discretize it as like u plus I plus 1 minus ui over delta x, right? Very, very simple, crude kind of discretization. So this is going to give you an order, like how much, what is the order of this discretization. It's always going to have some error, right? Whatever discretization you do, you are going to get some error for estimating these derivatives, right? So for example, if you have a continuous function, you can just get this this part and this part, right? If you discretize it, and so you are going to estimate this function with this line, and so this is going to be your error, right? This much you have error. So this is your error, right? But if you use a Fourier transform and take this derivative into the Fourier space in Fourier transform, what you are going to get is, based on this formula that we have for differentiation, is this, right? You are going to get minus I beta and Fourier transform of that. So you're going to get minus I beta and u hat of beta, right? So then here you don't need to do the discretization, right? You don't need to do the discretization in space. And so here, if you have a function that you solve, you don't have this problem, and you can just evaluate the exact functions here and here, right? So your solutions can become exact, unlike the if you calculate this derivative in the regular space. So this is like calculating derivative in regular space, and this is like calculating derivative in Fourier space. So you can get exact solution here, and you don't have any order of error. So this is also very useful for as I said, for numerical solutions, in addition to the analytical solution that we are going to introduce here. Okay, thank you very much, everyone.